You know, every single day, we're flinging trillions of bits of data across the globe. We're talking emails, photos, bank transfers, the whole shebang. And we just take it for granted that it all arrives perfectly. But what if it doesn't? So today, we're going to pull back the curtain on the invisible guardians of your data. These super clever mathematical tricks that are constantly detecting and even correcting the errors that threaten our digital world.
Okay, let's just dive right in. Take a look at the text on your screen. Now, you can probably make out what this is supposed to say, right? Our brains are just incredible at filling in the blanks. But a computer? No way. It would be totally lost. This right here is a perfect example of data corruption, and it's a huge, huge problem for any kind of digital communication.
So how does this even happen? Well, data can get scrambled for a couple of big reasons. Think about it. As data zips through cables, it can get hit with electrical interference. Or when it's bouncing around the internet in what we call packets, bits can just get lost or jumbled up. Either way, the result is the same. The data that shows up isn't the data that was sent.
So how do we actually fight back against all this digital chaos? Well, the very first line of defense is one of the oldest and, honestly, simplest tricks in the book. It's called the parity check.
And the core idea? It's actually brilliantly simple. Before you send your data, you just add one extra little bit of info, a single bit, whose only job is to be a lookout. And we call this the parity bit.
All right, let's see how this thing actually works. Imagine this is a byte of data, a little string of ones and zeros, all ready to be sent out. Before it goes anywhere, the computer sending it does a super quick count of all the ones. In this case, let's count them up. Yep, we've got 4 of them.
Okay, now here's the clever part. The sender and the receiver agree on a rule beforehand. Let's just say they agree to use something called even parity. All this means is that the total number of ones in the message, including our new parity bit, has to be an even number. Since our byte already has 4 ones, which is even, the system just tacks on a 0 as the parity bit to keep that total count even. Simple.
Now imagine that byte is zipping across the network and bam, a single bit gets flipped by some random interference. The data arrives at its destination. The receiving computer does the exact same check. It counts the ones. But wait, now there are 3 of them. That's an odd number. The even parity rule has been broken. Boom, the alarm bells start ringing. An error has been detected.
This seems like a pretty great system, right? It's simple, it's fast, but it's got a huge critical weakness. What happens if it's not just one little bit that gets flipped? And here it is, the fatal flaw. If 2 bits flip, say a 0 flips to a 1 and a 1 flips to a 0, what happens to our count? Well, the total number of ones goes from 4 to still 4. The parity is still even. So as far as the check is concerned, nothing went wrong. And just like that, the error slips right by, totally invisible.
Okay, so clearly we need something a bit beefier. And that brings us to a system that can not only spot an error, but actually find it and fix it. This is where parity blocks come in.
So instead of just looking at one line of data, a parity block is way smarter. It arranges a whole chunk of data into a 2-dimensional grid, kind of like a spreadsheet. Then it runs a parity check on every single row going across and another one on every single column going down. Okay, check this out. A block of data has just arrived. The computer runs its checks. Uh-oh, the parity check for row 8 fails. It has the wrong number of ones. And the parity check for column 5 also fails. It's kind of like a game of Battleship, right? We've totally narrowed it down.
And this is the aha moment. If we know the error is somewhere in row 8, and we also know it's in column 5, there's only one place it can possibly be, right where they cross. The system has pinpointed the exact bit that flipped, and now it can just automatically flip that 1 right back to a 0, correcting the data on the fly. How cool is that?
So that's a fantastic way to handle errors that happen during transmission. But there's another huge source of bad data that has nothing to do with electrical interference or network glitches. It's us, people. What about the mistakes we make all the time?
And that's where our final guardian comes into play, the check digit. This whole system is built specifically to catch the common, silly mistakes we make when we're typing in a long string of numbers.
Come on, we've all done it. You know, you go to type a 0, but your finger slips and hits the 2. Or you just swap 2 numbers around. That's called a transposition error, and it's super common. Or maybe you add an extra digit by mistake or leave one out completely. Check digits are the safety net for exactly these kinds of human fumbles.
Oh, and trust me, you have seen these things everywhere. Just grab any book and look at the barcode on the back. That 13-digit number is its ISBN, its unique identifier. And see that very last number on the end? Yep, that's a check digit. Now, that last number isn't just random. It's actually calculated using a very specific formula based on the first 12 digits. Basically, the system goes through this little mathematical dance, adding the digits in the odd spots, then adding and multiplying the digits in the even spots, and it combines them in just the right way to generate one final predictable digit.
What this whole calculation does is give the entire 13-digit number this special mathematical property, or a kind of superpower. So when a cashier scans that barcode or you type it in online, the computer instantly performs the exact same calculation on the first 12 digits. If the number it comes up with doesn't match that 13th digit on the book, beep, it knows you made a typo and tells you to try again.
Okay, so let's just step back for a second and look at the big picture here. What have we really been talking about this whole time?
Well, when you think about it, we've gone from a simple single bit acting as a lookout to a clever grid that plays Battleship with errors, all the way to special formulas that guard our barcodes. All of these methods are part of this constant, unseen safety net that really truly holds our digital world together.
So what's the big takeaway from all of this? These systems are absolutely everywhere, silently working in the background, making sure the information we rely on every single second is accurate. So the next time you scan a product at the store or just send a simple message, maybe you'll remember the invisible math that's always on guard duty, protecting your data and making sure everything just works.